Hello, welcome to Fuzzy Logic. Today we would like to discuss about some applications that used fuzzy logic in order to make ease their work. First is Traffic Light Controller. This is an application of fuzzy logic for multi-agent-based autonomous traffic light control system using wireless sensor. The linguistic inputs for Traffic Light Controller are QUECE length and traffic density, while the output is cars waiting time. For example, if QUECE length is long and traffic density is high, then the car's waiting time will become short. Next, we are going to discuss about the automated room light controller. The number of people and light intensity are the inputs for this system, while the light intensity is its output. For example, if number of people is many and light intensity is bright, then the light intensity will change to very bright. Let's see the condition. First, there is no people in the room and the light intensity is bright. After 3 persons enter the room, the light intensity will change to very bright because the light intensity will be changed by sensing the number of people. This may help us to increase the lamp life and save electricity costs. What are the components that used in automated room light? There are 2 components, which are sensor system and microcontroller. The sensor system can be used to measure room light intensity and detect the number of people. Lastly, we will talk about a fuzzy decision support system, which is DSS, for management of breast cancer. The linguistic inputs for this system are human epidermal growth factors, receptor 2, risk age, hormone receptors, tumor grade, tumor size and lymph node. Based on the 6 inputs, we will get the output, which is the risk status of people to get breast cancer. For example, if HER2 is negative, hormone receptors is weak positive, the age is high, grade equal to 1, size is small and lymph node is equal to 0, then the risk status to get breast cancer is low. Otherwise, if HER2 is positive, hormone receptors, age, grade, size are equal any value and lymph node is intermediate number, then the risk status to get breast cancer is high. Thank you.
Created using Powtoon.
In artificial intelligence, the ultimate quest is for machines that think like humans. One man recognized that the only way to truly think outside the box is to do away with the boxes themselves. By abandoning the rigid idea of true or false, Lotfi redefined how we think about logic. He faced staunch opposition along the way, but ultimately became the father of fuzzy logic. Countless intelligent products can process the same kind of imperfect information we use to navigate an ambiguous world. They do it by using fuzzy logic, a deceptively simple yet powerful idea that was the brainchild of one radical thinker.
My aspirations were not to become rich and powerful, but to be driven by a quest for contributing to society, to improvement of society.
Lotfi learned to overcome obstacles early, when, after completing 3 years of elementary school in the Soviet Union, his family moved to Iran.
By mistake, I was admitted into 8th grade, from 3rd grade to 8th grade.
Somehow Zadeh managed and went on to study electrical engineering, graduating from the University of Tehran in 1942.
I could have stayed in Iran, I had a very good life, but it would be the life of a well-to-do person with nothing serious to do.
When Zadeh was offered a chance to be a graduate student at MIT, he took it. When he got to the States, he looked up an old family friend.
He came to visit me in New York because he was very lonely when he came from Iran. And as I opened the door, he took off his hat. And I said, "Ah!" because he had no hair at all.
3 years later, Zadeh had a new wife and a master's degree from MIT. He went on to Columbia for his PhD, where he would remain for 17 years. He then moved to Berkeley and was named chair of the Electrical Engineering Department in 1963. While attending a mathematicians' conference, a simple idea occurred to Zadeh about the nature of sets, groups of objects or numbers considered entities unto themselves.
If you look at the real world, you find that most classes, the class of beautiful women, the class of large countries, the class of small apples, are too precise. You have to generalize that and introduce a class whose boundaries are unsharp.
With the publication of his first paper on the topic in 1965, fuzzy logic was born. Zadeh reasoned that people don't require precise numerical input to make decisions, so why should computers? What if systems could be programmed to accept noisy, imprecise input? Initially, the theory was met with skepticism and even hostility. Its biggest problem was perhaps its name.
I knew that fuzzy is not a good word. I knew it very well. But I did it, and I never regretted my choice to this date.
Even decades later, in certain arenas, fuzzy remains a bad word.
The image is that of some sort of a logic that is not precise, that is muddy. But in fact, fuzzy logic is precise. It's a precise logic of imprecision.
By the early 70s, the theory began to gain acceptance, and fuzzy logic products started to pop up everywhere, particularly in Japan. It was integrated into everything from civil engineering machines to household appliances. Today, most consumer products use some form of fuzzy logic.
This camera, this probably uses fuzzy logic, you see.
Fuzzy logic not only makes better machines, it touches on how we understand language and culture.
In fuzzy logic, everything is or is allowed to be a matter of degree. So this is a big thing.
Zadeh has made a career out of bucking convention and faced opposition every step of the way. But today, he can look back with pride and perhaps a bit of vindication.
Of course, I'm not immune to making wrong decisions, wrong predictions. But for the most part, I can sort of pat myself on the back and I say, yes, that I was right.
The 2009 Benjamin Franklin Medal in Electrical Engineering is presented to Lotfi Zadeh for his invention and development of the field of fuzzy logic, a mathematical system that captures aspects of the ambiguity of human language and thought, which has solved problems in areas such as artificial intelligence and the automated control of machines.
We had a seedling fund, which we competed against 300 and some other proposals and were selected and teamed with the National Test Pilot School in California to try to demonstrate the kind of a large global type nonlinear aerodynamic modeling capability, which we think the fuzzy logic algorithms can do. We picked a little jet that can fly an unrestricted envelope, and it was instrumented already, and got some data with that, and then tried out the fuzzy logic approach. And it looked like the modeling was very successful. And what the fund from the center sort of sponsored was to see if we could go backwards from that. Now take the model that we just, the mathematical model, and put it in a simulation and see if we can make it fly like the airplane. We developed those fuzzy logic models from the flight test data and then went over to the differential maneuvering simulator and tried to develop the equations of motion. We didn't spend a lot of time and a lot of money to do it, but we got our quick look results that, it does look airplane-like. You could fly it and spin, things like that. And there's still some things to work out, but certainly looks like it has promise at this point. What makes it special is the nonlinear modeling. And we developed the flight test maneuvers as well as the algorithms to analyze those. So it makes flight testing much more efficient if this kind of a technique works. Much cheaper. You can get a high fidelity model over a large range of flight conditions very quickly, which is very unusual for standard flight test methods. There's a lot of applications. One in flying, if you want to fly an airplane and it has some problem, has a failure of some sort, not only can it tell that it has a problem, but it can tell what the problem is, how it's changed its dynamic capabilities. If you're a piloted airplane, you can use that to warn the pilot and give him new cues of how to fly the airplane. If it's a UAV or an autonomous airplane, it can reconfigure and fly itself in the best way it can to try to survive the mission, that kind of thing. Additionally, this kind of techniques help in development of an airplane, such like wind tunnel testing. Next session, we have a computer that's mounted in the back seat so that we can get real-time maneuver guidance and also be developing the models while we fly.
Fuzzy logic is a way of dealing with uncertainties, which isn't something that computers do naturally, but something that humans deal with very well. So normally when we think of logic and when we think of reasoning about things, the way computers tend to deal with things and the way you might instantly think of dealing with things is true and false, 1 and 0. So for example, you might classify someone who's watching computer file as watching it, true, or not watching it, false. It's very simple. There is only one option or the other. We have no in between. That's not the way that the real world works, and that's not the way that humans work. So you can look out of your window now and you can say today's nice weather, or if you're in England it's likely not nice weather, but the definition of nice varies from person to person. With fuzzy logic, instead of just going with true and false, 1 and 0, we have a sliding scale. We have between that, we have what's called a degree of truth. So I can look out the window and say that today is kind of iffy, it's a bit sunny, but there's some clouds. Maybe it's 0.3 nice day or 0.7 nice day.
Is this about like the saying, there are no grey areas, it's either black or white?
Exactly, yeah, there are always grey areas. And the grey areas vary from person to person, which we'll come back to later. So logic is also very closely related to sets, and a set is a collection of things. So when we talk about something being true or false, we also talk about there being a set where something is true, and if it's not true, they're not in that set. So the set of nice weather, if I was going to describe nice weather, I would probably decide that I don't really like things too hot, so Nice is when it's cold, but cold enough to not wear a jacket, but not too hot for me to feel uncomfortable. So that would be what we'd call the membership function. That gives a value for a certain thing. So if I check the temperature and I see that it's about 18 degrees, there's no wind, then that probably fits into a 1 on my niceness scale. If it's no clouds at all, there's no shade anywhere, it's 30 degrees, that probably is closer to a 0 on my scale. So you get nice sliding graphs. That gives us a way of dealing with uncertainty. So if we look at this example on the board. So this is kind of the typical example for fuzzy logic, which you see everywhere. This could be a shower controller. So with temperature, things don't just suddenly go from hot to cold. You have different scales. So what we'd have here is 3 of these membership functions that assign things to different values. So for example, at a low temperature, we know that it's cold. As the temperature goes up, it gets less cold, and then we start to see warm kicking in. So around, I don't know, we can decide this is probably about 15 degrees. I haven't put any actual values on here. So around this area, we now know that we're kind of mixing warm and cold. It's not strictly cold, it's not strictly warm. And then we have the same story with hot. So this gives us a way of dealing with the fact that the temperature of water isn't a strictly Boolean thing. It's not strictly true or false. If we look at the shower controller, we know that at some point, someone has decided this is now no longer cold. And this is where warm starts kicking in. So although we're dealing with uncertainties and we've got these membership functions that allow us to model them, you still have someone imposing their definition of that word onto it. Someone still needs to decide the values of the membership. And that's where things get very complicated. And when you're dealing with fuzzy expert systems, you often need to collect data from many sources, and you have to use various techniques to consolidate that data and to train the system to be as accurate as possible. Okay, so when we talk about a fuzzy expert system, we're basically talking about a fuzzy system where the membership functions and the values we're using have been fed in by experts in some domain area. So in our example, it would be experts in knowing what people like in their showers. They will decide at a certain temperature, this water is no longer cold, and it starts to get towards warm and pleasant. Fuzzy logic systems which use membership functions like this and have these fuzzy sets and have these degrees of truth are very widely used in all sorts of things you might not expect. When you set the setting on your washing machine, it doesn't just do it exactly that same way every time. It checks the load of the wash, it checks how dirty the water is after each cycle through. It does all sorts of things to decide exactly what temperature and exactly how fast to spin to make sure that it's as eco-efficient and giving as good a wash as possible. One of the most famous examples of a fuzzy logic system in use is the Sendai Railway in Japan. So this is a subway which is one of the first uses of fuzzy logic that actually measures the weight on the train, how fast it's going, suspension and all sorts of these things to make sure that it maintains a level and smooth travel. This diagram here is kind of showing a rough outline of a fuzzy logic system. We have an input which takes in crisp values. So these are things which aren't yet assigned a truth value. They're not in a fuzzy set, but then we fuzzify them. So we look at our membership functions and we apply some value to them. Then we have our fuzzy sets, and these go into our inference system. This is where all the magic happens. This is where we then start to reason. So we have a rule base, and a rule, if I quickly draw this on the board. So a rule has the form of an antecedent, then a consequent. If water is dirty, then, and then this will also be a fuzzy set. So water is dirty. This is a fuzzy set. So we're looking at our water, which will probably come from here, and we'll check it against the dirty membership function. So if we go back to our shower control example and think about that, we might say if water is warm, and we check how much it's warm. So say dirty, we had a membership function that some sensor was checking the water to see how dirty it was, and if it was pitch black and the sensor detected that it was very dirty, we could say that this is 1. So then we'd act on it in some way. So we then might say some other fuzzy set is a certain value. So we would say, then spin very fast, or add detergent, or do another rinse cycle, any number of actions. And that gets on to the next point. So we actually have a rule base. There's multiple rules for different membership functions, for different actions, different outputs. And we run all of these rules through them, and then we combine them in this inference engine. This is what the inference engine does. It takes these rules, it applies the fuzzy sets to them, and it combines them to come up with some output, some decided action. This decided action is in the form of fuzzy sets. It then gets defuzzified because computers, as I mentioned earlier, they deal in certainties, they deal in true and falses, they deal in zeros and ones. We need to defuzzify them to something that the system can use. So we defuzzify it and we get crisp values as output. So that's some action. So go back to the washing machine, we take in some measurements of the water temperature and how dirty the water is. We apply those measurements to our fuzzy sets, so we know some information about, so we have some fuzzy information, some truth values about how hot and how dirty the water is. We then check those against our rule bases, and we decide on some actions. We decide how fast it should spin, how much water should be in the next rinse cycle, how much detergent we should mix in. We remove the fuzziness from that, we give a crisp value as output, and then that action is undertaken by the system.
How does it work when it's not using fuzzy logic?
We'd probably end up taking our measurements, our crisp values, and instead applying an awful lot of if statements to them. So, I don't know, if I rub this out and, if temp is less than 30 and dirt is greater than 6, do rinse cycle, or something like this. And you'd have to do this over and over again. Once we have all these rules built up that build on this, it looks very similar to our rule base, but the difference here is that because we're describing these here and we haven't done anything with this before, we're describing these conditions here and we haven't done anything with these values before, it's almost as if we're defining our membership function in the conditions, and it's a much less concise way of dealing with things. It's not as easily maintainable and changeable in code. It's just a bit messy, to be honest. And if you decided at some later date that your washing machine would be more efficient if you'd done a temperature value differently or a dirt value differently, it'd be much more hassle to go back through it and change it all, and the system would be much more maintainable. Whereas in this way, we don't have to change the rule itself, we just change our definition of dirty. Our use of it is somewhat hypocritical in that we don't deal with all uncertainties. Our measurements might be uncertain, our definitions might be uncertain. So there's continuing advancements in describing these uncertainties better. But the big problem is once you start dealing with more uncertainties, the computational demands start to really build up. And that's the current area that is being tackled, as well as there's numerous areas. It's a very heavily researched topic, and it actually has probably one of the largest abundance of published papers for any individual topic.
You're trying to access this bit of memory, but that's not your memory. That doesn't belong to this program.
There's a little program which I've written already.
It's not happening, and so the operator.
Anyone which is familiar with BASIC will understand all of that.
Welcome. In this video we talk about fuzzy logic, a tool engineers and scientists use to add intelligence into robots, video games, and even in household appliances. Fuzzy logic is fantastic as it solves complex problems by using simple rules. Let's see how an intelligent robot tackles the challenging task of boiling an egg using fuzzy logic. Boiled eggs are popular for breakfast worldwide. Boiling an egg sounds trivial. However, only a few have mastered the art of preparing the perfect soft-boiled egg. This is Jane, a robotics engineer. She will help us with the robot design. Initially, Jane had designed the robot according to her grandmother's recipe book.
Drop them in boiling water and remove them after 5 minutes.
Unfortunately, the eggs sometimes turned out too soft or too hard. Jane decided to ask her best friend Mike, who is a chef, for some tips. Mike noticed that Jane's robot didn't consider the egg size when deciding the boiling time, so he gave Jane 2 simple rules to follow. If the egg size is small, then boil for less than 5 minutes. If the egg size is large, then boil for more than 5 minutes. But Jane thought,
What does small, large, less or more mean? We know that egg weights can range from 40 to 70 grams, with boiling times ranging from 3 to 6 minutes.
Fuzzy logic utilizes this knowledge. Designing the intelligent egg boiling robot requires 3 steps: fuzzification, inference, and defuzzification. Step 1. Fuzzification. The robot takes an egg and measures its weight. According to fuzzy logic, any egg is both small and large, but to different degrees. For example, our robot considers a 50-gram egg as small in a larger degree and as large in a smaller degree. Those are called fuzzy values. Step 2. Inference. Since the egg is both small and large in different degrees, the robot applies Mike's 2 rules. but again in different degrees. Step 3. Defussification. The robot must now calculate the actual boiling time based on the fuzzy values from the previous step. Hence, for the 70% less and 30% more than 5 minutes boiling time, a balanced decision would be to boil the egg for 4 minutes. Our intelligent fuzzy logic egg boiling robot is now ready.
So what is fuzzy logic? Well, first let's think about traditional logic. In traditional logic, something can be represented by either having a value of true, which is 1, or false, which is 0. In fuzzy logic, you can be anywhere in between 0 and 1, so you could have something that's true, but only partially true, with 0.7, or false, it's mostly false, with 0.3. So let's use tap water temperature as an example. In traditional logic, you would have this represented by either being hot or cold, representing 0 or 1 respectively. With fuzzy logic, you could have something like this, where you have a gradient from hot to cold. So you could have something that is lukewarm, very hot, slightly cold, etc., instead of just hot or cold. So why is it useful? Well, consider you have an automatic braking system in your car that can decide when to brake. Using traditional logic, it might look something like this, where you have a car in front of you that's far away or close, and there's some value in between where it switches. The car being close can either be yes or no, 0 or 1, and the brakes can either be on or off, again 0 or 1. So in this situation, the car is far away, so it's not close, and the brakes are off as a result of this. Now in this situation, the car is now close, represented by 1, and the brakes are now represented by 1 as on. Now this might be a problem because the car is now applied the brakes with full pressure, and you're going to slow down very quickly, even though the car in front of you might not be approaching you very quickly, it might not be moving at all. And this puts huge stresses on the car, including the components like the suspension, the frame, not to mention the occupants. So instead of doing something like that, let's consider using fuzzy logic. So this is your situation, and now, going from close to far, you have this gradient. And you can say, is the car close? Well, it's anywhere between 0 and 1, this range. And the same thing with the brakes, you can apply pressure between 0 and 1. So in this situation, is the car close? Well, 0.2. It's not very close. And as a result, the brakes, we're only going to put slight pressure on. And in this situation, is the car close? 0.8 is pretty close. And as a result, the brakes, we're going to apply fairly heavy pressure to. And this will slow us more quickly. The result of this is that you get a much smoother output depending on where the car is, and it's not just on or off for your brakes. This will put less stress on the car and the occupants. So how is it different? Well, with traditional controllers, you need to know detailed physical properties of the system, and this can be difficult. And most systems are too complex and have to be idealized to develop a traditional controller. What this means is that you don't have a full representation of the system when you design your controller. And the conditions when traditional controllers will work is usually fairly limited. Fuzzy logic controllers, on the other hand, you don't need to know much detailed knowledge of the system. And what the controller should do is determined by linguistic rules, and this is very easy to do for humans that know what the controller should do in certain situations. And if optimization tools are used like genetic algorithms, you can get away with not knowing much of anything about the system. The system also doesn't need to be reduced or idealized to develop a working fuzzy logic controller. And the conditions when fuzzy logic controllers will work are more robust because they can account for more variability in the inputs. So what is its potential? The number of applications are virtually limitless. You could have control systems, like kitchen appliances. You could also have car control systems, aerospace vehicle control systems. Fuzzy logic can also do image processing, decision making, route planning, and it's still in development and testing for safety critical systems like autopilots, although it has been tested and implemented in some small instances like small satellite attitude control. But remember with fuzzy, the sky is literally not the limit.